In the previous lectures, we discussed about an ideal transformer, turns ratio, primary, secondary, term. In today's lecture, we will be discussing about the non-ideal transformer. That means a practical transformer. What will happen in a practical transformer? So when we are exciting the primary of the transformer, we have primary winding of the transformer. We have secondary winding of the transformer. Okay, when the primary winding is excited with an voltage of V, a flux will be established in the magnetic path. Okay, a flux will be established in this magnetic path. This established flux phi m or phi links with the secondary winding in order to induce the secondary EMF. That is how transformer works. So in no load, when there is no load, there will be a minimum current. A current will flow through the primary winding required to establish this flux phi m in the magnetic core. So this current is known as magnetizing current, magnetizing component of current or magnetizing current. Okay, so we know that the induced EMF in a transformer is equal to root 2 pi fn1 into phi m, Therefore phi m, we can write it as phi m is equal to E divided by root 2 into pi into f into n1. Okay, so if we neglect the winding losses, this E will be is equal to V. Okay, this V will be is equal to the applied voltage V. Okay, therefore this will be the flux in the current. Okay, so we know that the flux phi is equal to Ni divided by reluctance R. Okay, Ni divided by reluctance R, where N into I is the MMF, R is the reluctance of the circuit. This reluctance can be written as Li divided by mu naught mu R into Ai into N. Okay, where A is the area of cross section, where area, there is no N, Li divided by mu naught mu R into Ai, where area is the area of cross section, Okay, substituting this equation in the above equation, we can write I is equal to first deriving for I is equal to R reluctance into phi divided by N, and substituting for this R we will get this one. So magnetizing current Im is equal to phi m into Li divided by mu naught mu R into Ai into N1. So this magnetizing current depends on number of turns, depends on area of cross section, depends on the permeability of the material, where mu R is the permeability of the material. So magnetizing current, in order to establish, will vary on the magnetic material used in the transformer core. Okay, and this magnetizing current is directly proportional to the flux induced in the magnetic core. This magnetizing current is directly proportional to the flux induced in the magnetic core. So we know that phi is equal to phi m sin omega t. I will be equal to magnetizing current Im sin omega t. Magnetizing current I will be equal to Im sin omega t. So we can say that this phi m and Im are in phase with each other. This Im magnetizing current is in phase with the flux produced in the transformer. So by representing it can be represented in the vector diagram like this. If the vector diagram is shown here, it can be represented along with the flux phi m. As you can see here, it is represented along with the flux phi m. This is Im, which is represented along with the flux phi m. We know that flux will be varying by an angle of 90 degree from the applied voltage, and the induced EMF E is equal to negative of E1. Therefore it will be in the opposite direction of the applied voltage V1. So induced EMF E is in the opposite direction. The EMF induced in the secondary will be in the same direction of the induced EMF in the primary, and flux will vary by an angle of 90 degree to the applied voltage and to the induced EMF. Therefore this Im will be in phase with the flux phi m. So when transformer is loaded, that means a load is connected to the secondary of the terminal. Primary is excited by an voltage V, and load is connected to the secondary of the terminal. So we can write this will be the primary of the transformer core, this will be the secondary of the transformer. When there is a load here, the current load draws some current from the primary winding, secondary winding to the load current. So in the primary there will be magnetizing current, which will be flowing in order to induce the in order to establish the flux in the magnetic core. Okay, when this current is drawn, MMF will be induced in the opposite direction, and an MMF in the core will be induced in the opposite direction, which will reduce the flux, in the magnetic core. Flux is reduced when we can write it as when secondary current is increased, flux is reduced. Flux in the magnetic core path is reduced. Therefore, in order to maintain this flux constant, this primary current will increase. Okay, it will draw more magnetizing current. This Im will increase. Okay, in order to maintain this, retain the magnetizing flux or maintain the flux constant, it will draw the magnetizing current. So the current drawn from the primary I1 will be equal to the magnetizing current which is required, and an equivalent current which is drawn from the secondary, so we can call it as I2 dash. So I1 will be equal to Im plus I2 dash. So as we know that this Im is lagging by an angle of 90 degree with the applied voltage, this Im is lagging by an angle of 90 degree with the applied voltage V1. Therefore, it can be represented as a form of an inductor in the primary circuit. It can be, as we know that in an inductor, current lags the voltage by an angle of 90 degree. It can be represented as pure inductor in the primary circuit of the transformer. So as you can see here, this is I1. This is the magnetizing current Im, which is going through the inductor XM connected to the supply V1. So in this case, as there is no load connected, I2 dash secondary equivalent in the primary winding is equal to 0. Therefore, I1 is equal to Im. This is during no load condition. An equivalent circuit with respect to the primary can be written like this.